Have you ever stopped and wondered how your computer actually thinks? You know, how it can take a photo, a song, or even just text and actually understand it? Well, it all boils down to a kind of secret language, a language made of numbers. So let's dive in and decode the number systems that pretty much power our entire digital world. It all starts with a super simple idea. Look at your hands. We have 10 fingers, right? That's almost certainly why, as humans, we ended up with a counting system based on the number 10. It just makes sense to us. But computers? Well, they don't have fingers. They have switches. So what do they count with? Before we can really get a handle on the computer's world, we've got to get crystal clear on our own. The system we use every single day without even thinking about it is called the decimal system, and it is built completely around that magic number, 10. And the key concept here, the thing you gotta know, is something called a base, or if you want to be fancy, a radix. It's just a term for the total number of unique digits a system uses. For us, in our decimal system, the base is 10. Why? Because we use 10 digits, 0, 1, 2, all the way up to 9. Now here's where it gets really cool. It's not just about which digits you use, it's about where you put them. Take the number 125. Each digit's position gives it a specific weight that's based on a power of 10. The 5 is in the ones place, the 2 is in the tens place, and the 1, that's in the hundreds place. It's this whole system of positional weight that makes it all work. Okay, so our system is built on our 10 fingers. A computer system, though, is built on its own physical reality, which is billions and billions of tiny little electronic switches that can only ever be in one of two states. And this just lays it all out perfectly. On the left, there's us, with our 10 options from 0 to 9. But look at the right. That's the computer's entire world. Its switch is either on or it's off. There is no maybe. We just represent those two states with a 1 and a 0. And that's it. That is literally all a computer has to work with. And this system, this simple on-off 1-0 system, has a name. It's called binary. Since it only has two digits, it's a base 2 system. And this is the absolute fundamental native language of every single digital computer on the entire planet. So we've got our comfortable world of decimal, base 10, and the computer's world of binary, base 2. But as you can see here, there are a couple of other really important players that programmers use all the time. Octal, which is base 8, and hexadecimal, which is base 16. And we're going to see exactly why these are so incredibly useful. So, if we think in decimal and computers think in binary, how in the world do we communicate? Well, we have to translate. We need a way to convert our numbers into their language and their language back into ours. Alright, let's start by translating from the computer's language back to ours. The logic is actually the exact same as our own decimal system, but instead of weights based on powers of 10, we're going to use weights based on powers of 2. You just assign the weight to each bit, multiply, and then add the whole thing up. Let's see it in action. Okay, let's walk through this one. We have the binary number 101011. See how we start from the right? That first 1 gets multiplied by 2 to the power of 0. The next 1 by 2 to the power of 1, and so on all the way down the line. We do that for every single bit, multiplying it by its positional weight. Then you just add up all those results, and boom! The computer's 100111 translates perfectly to our number, 43. So how do we talk back? How do we go from our numbers to the computer's? Well, for this, we use a really clever little division trick. You just have to keep dividing your number by 2, and, this is the important part, keep track of the remainder. Let's try it out with 125. As you can see, we divide 125 by 2. That gives us 62 with a remainder of 1. Then we take that 62, divide it by 2, that's 31 with a remainder of 0. You just keep doing this over and over, all the way down until you hit 0. Now here is the secret sauce. You have to read those remainders from the bottom up, and when you do, you get the binary number 111-11101. So you can see how binary is absolutely perfect for computers. But for us humans, all those ones and zeros, they get ridiculously long and just impossible to read. We needed a better way, some kind of shorthand. Seriously, just try to imagine reading or typing 100 ones and zeros in a row and not making a single mistake. It would be a total nightmare. And that exact problem is what forced programmers to find a more compact, more human-friendly way to represent all that binary data. And this is where hexadecimal just shines. It is such an elegant shortcut. You take that big, ugly binary number and you just break it into little groups of 4 bits. And here's the beautiful part. Because 16 is a power of 2, every possible 4-bit chunk maps perfectly to a single hexadecimal digit. It's just a clean one-to-one translation.
And this is where the magic happens. Look at that long binary string, 101111101. Okay, let's group it into 4s from the right. The first group is 1011. In decimal, that's 11, which is the letter B in hex. The next group is 1011 again. Hey, another B. And the last little bit is 10, which we can think of as 0010, and that's just 2. So that crazy long binary string becomes the simple, easy-to-read hex number 2BB. It's the exact same information, just way, way easier for a person to look at.
You know, the octal system is built on the exact same idea. It's also a shorthand for binary. The only difference is, instead of grouping bits into 4s like you do for hexadecimal, with octal, you group them into 3s. It's not as common these days, but it was a big deal in early computing, and it's another great tool for making binary manageable.
Okay, so we've been deep in the weeds with different bases and conversions, but let's pull back for a second. What's the big picture? Why does any of this actually matter? Well, it matters because these number systems are, quite literally, the building blocks of your entire digital life.
Think about it. At the most fundamental level, every single piece of information on your computer, the music you're streaming, the video you're watching, the graphics in a video game, even the letters that make up this very sentence, it's all stored and processed as just a long, long sequence of 1s and 0s. It's all just numbers. This right here is probably the single most important idea to take away from all this. The entire incredible complexity of our digital world, all of its color and sound and information, it's all built from the simplest possible foundation you can imagine. A system with only 2 choices, on or off, 1 or 0. So think about it. The next time you're on a website and you see a color code, that 6-character mix of letters and numbers, you'll know what it really is. It's just a hexadecimal shorthand for 3 binary numbers that are telling your screen exactly how much red, green, and blue light to mix together. It's all just numbers. Which kind of leaves you with one final question, right? What else in your digital life is just numbers and